Welcome back to the second part of the video or the tutorial on Minkowski Sum. My name is Ari Berestiano, and we continue from the point where we stopped last time in the previous video. Here is the definition of the Minkowski Sum. Now we want to look at some properties which are a little bit more complicated and a little bit more interesting and related to the field of partial identification that uses Minkowski summation in econometrics. Okay, so first of all, we look at some papers in partial identification. You will see the Minkowski average. So think about a sequence of sets, A1 all the way to AN, sample, for example. We would define a bar, the average of those observations, to be 1 over n, okay, the number of, okay, and then we will do the summation. Okay, and we'll say I from 1 to n of AI. And this is, by our definitions before, well-defined concept. Okay. Second thing that is going to be useful when you think about partial identification is the following property. Okay, and I'll number it as number 5. The convex OR, okay, convexifying the Minkowski sum of A plus B is equal to the convexification, convex hull of A plus convex hull of B. And as a conclusion from number 5 here is that if A and B are convex, okay, also A plus B Minkowski sum is convex, the convex set. Okay, great. The other thing worth mentioning here, okay, is that number 6, okay, if A and B are compact, A plus B is compact set. Okay. Again, this is a very these two are very good properties. Why do we need 5 and 6? Again, if we make a collection of sets, okay, we don't want to talk about all the possible sets. Let's define by K and subscript C, okay, of Rk, okay, to be the collection of all compact convex subsets of Rk. Okay, so compact convex subsets of Rk. Okay, so what we have from 5 and 6 is that if we take two sets from this collection, the sum of them is also a member in this collection. Okay, so that's a good property to have. Now here are some quirks and some things to keep in mind about the Minkowski sum. Here is a question. Okay, question. If A is in Rk, okay, in our case, so our set here is some set. I didn't say anything about it. And I'm looking at A, Minkowski sum A. Is it equal, I'll put here a question mark, is it equal to 2 times A? Okay, we would like something like that to be true. So in general, okay, the answer is not necessarily. Okay, but more precisely, the above is true. Okay, if and only if A is convex. Okay, the one if is just a result from 5, but the other direction is correct as well. Okay, so again, this is a good collection to think about when we think about Minkowski summation. because it's closed under and some reasonable properties are being satisfied. Okay, so let's think about some other properties or potential properties of the Minkowski sum. But first of all, let's see what if we take the ball, which is centered in the point C1, a point in Rk, and has a radius R1, and sum, okay, plus here, another ball, which is centered in another, potentially another point C2, and has another radius R2. Okay. Now, when I say ball here, okay, I need to go back to the fact that I measure distance by the Euclidean distance. Okay, so it's really the ball the way we think about a ball. So since both of them are compact, convex, the sum is going to be the same, but more precisely, in this case, as we would like, it's going to be the ball center at C1 plus C2, which will have a radius of R1 plus R2. Okay, and that's nice, and we like that. Now, okay, we sum two circles, and that's a good result. But what if we take, and now I'm going to, instead of writing formulas, let's do a picture. I'm taking a rectangle. Okay, let's say a rectangle that looks like this. And I want to sum, okay, Minkowski summation, some circle, some ball. And here I'm doing it in R square because that's how I want to picture it, or it's convenient to picture it. So here is another set that is a circle. Okay, how do I sum two very different sets doing the Minkowski summation? So now you need to imagine the following thing. Let's for example, take this tiny circle and put it on the outside, all the points in the outside of the rectangle, and just take and move the circle around the rectangle. Okay? What we do here is we take points on the outside of the box of the rectangle and sum to those points the circle. So what you will have here in terms of the result, okay, is, and that's, I'm going to try and picture it in a nice way. So I'm going to copy the rectangle, but in dotted. Okay, so imagine a replica of this rectangle, almost like that. Okay, like this. And then at each point, I'm adding on the frame here, I'm adding the circle, so I'm moving the circle around, moving in the circle all the way around like that, many times for all the points. So what I will have is the following shape. Okay, those will sum. I will have this rounded corner here, sum up to this point, a rounded corner going down, again a rounded corner here, and like that. So at a result, the shape will be everything. Okay, I will have to fill it, of course. And it will be a bigger rectangle with the rounded corners. The rounding comes from the fact that we are moving the circle around on the outskirts of that rectangle. Okay, so that's Minkowski summation in a graphical way here. So to wrap it up, let's think about the following question. Okay, Rk with the multiplication by a constant and the summation of two vectors is a vector space. Now we have this clause under summation for the compact convex sets, and the question that I want you to think about here at the end is the following. If I take the collection of compact convex sets, okay, let's write it like that, compact, okay, convex subsets of Rk. Okay. And I equip it with the Minkowski summation, Okay, so I know how to sum two elements of from this collection, and they will stay inside this collection. And I will equip it also with the multiplication, the regular multiplication by a constant from R. Okay, so it will be defined, this field defined on RK, on R and not RK, but let's keep it like that. Is this a vector space? Okay, and that's the question. Is it a vector space? So we covered some properties that show that almost all the properties that we ask from a vector space are satisfied for the summation and the multiplication. But there is one property which the Minkowski summation doesn't have. Okay, so pause the video, think about it, and try to go to the definition of what is a vector space and think about what there is missing. What are we missing? Okay, so if you thought about it and if you find it, the answer is that there is not an inverse operation. Okay, so suppose I am having or picking a set A from this collection, and I want to find another element in this collection that I will sum it to A, and I will get the 0. Okay, so for the summation, Minkowski summation, we already covered in the first video that the set containing the vector 0 is the 0 operator for the summation. Great. So can I find, if I have A, okay, can I find, and A is a sum set, can I find something to put here such that the summation will be equal to 0? And the answer is no. It's not possible. There is no minus A to add. Okay, so if you try saying, oh, well, I'll take A, okay, and sum it with a set which is minus A, okay, so I'm taking the number -1, multiply all of the elements in A. What will I get here? It's not going to be the set 0. That's not going to be right, unless A itself is a singleton, which is a very special case. But by and large, this is not true. Okay. So I will put at the end of or the bottom of below the video a link to a paper that tried to address this question: how can I subtract something from A such that I will be left with 0? And the answer there is partial. That's an issue always with Minkowski summation and working with sets. Okay, so that's it for this video on the topic on Minkowski summation. Thank you for watching, and leave comments and send me feedback on the topic on the videos, and I'll be happy to hear from you, and maybe suggestions for other topics that you would like me to talk about. Thanks.